This is last time where we left. We said that the disk has to be formatted before we start using it. There are two levels of formatting. One is the low level formatting, which is actually going over all the writable tracks of the disk, and for each sector putting this data structure in. Each sector is structured like this. So this part is a sector, this is another sector, this is another sector. It goes like that, and each sector is structured like this. We said at the beginning there is a preamble which contains information about the sector address, sector information, which cylinder it is, which platter it is, and which sector it is. It gives us this information and some other information too. And the data itself, depending on your disk structure, data could be 512 bytes or 1 kilobytes or whatever your disk controller decided to do. And at the end we have the checksum control, error control bits. Okay, so this information needs to be put in for all the places on my disk. Of course, at the beginning it is empty. The data doesn't mean anything, but we need to make sure that whatever we are writing, we can read the same thing. So low-level disk formatting includes that process. You write some data and you read it. You write again and you read it. And if you are writing and reading the same thing over and over again, then that's a good sector. I can use it. If it is not, then that's a problematic sector. Then in my preamble, I will mark it as this sector is not a good sector, and we are going to talk about it later. So disk is formatted this way. So each sector is given a number. You will say, okay, this is my sector number 14, 15, 16, it goes that way. It has to start from somewhere till 0. So it looks like this disk has 32 sectors for each track. Okay, but as you see, we are not starting from the same number when I go to the inner track, because my sector number 0 is here and it is here. This is called, as we last time we called it, it's called cylinder skew. Okay, this is the term, cylinder skew, and this is done because my disk is rotating this way. So that's the disk rotation direction. So it is rotating counterclockwise. If it rotates that way, okay, when I move from this track, when I move my read-write head from this track to this track, it's going to take some time to move my head, okay, read-write head. While I am moving my read-write head, the disk is rotating. So this means what? After I read sector number 31, okay, to be able to read the sector number 0 from the other track, okay, I moved my head, but my disk moved too. So I am adding for this one. So it looks like I have a skew of 1, 2, 3, 4, right? 4 sector skew. So I am right at the beginning of my next track. So if I have a sequential file, if I write my sequential file in this way from inner tracks to outer tracks, when I am reading my sequential file track by track, so this kind of accounts for the time lost when I am moving my read-write head. That's called cylinder skew. And of course it depends on how fast your read-write head mechanism is. Also it depends on how fast you are spinning your disk. I think we had a example here. Let's say my disk is spinning very fast, 10,000 rotations per minute. And that means what? Each rotation takes 6 milliseconds. Okay, if a track contains 300 sectors, so around my track there are 300 sectors. To read a sector, I need 20 microseconds. And if my read-write head is taking 800 microseconds to move one track to another track, that means what? when I spend this time 800 microseconds, that means 800 over 20, 40 sectors will pass under my read-write head. So my cylinder skew should be at least 40 sectors. If it is not, then what? What is the penalty? If I don't use 40 sectors as cylinder skew for this case, let's say my cylinder skew will be 0. I use the exactly same numbers for the, it's going to be like, if these are my tracks, if this is my sector 0, if this is 0 and if this is 0, okay, this is skew 0, right? So what would be the penalty for this case? Every time I move my head for a sequential file, I am going to lose 6 milliseconds, right? Because I have to wait another rotation to get to my desired sector. Okay. Of course, these are all for the sequential files. For the random files, random access files, doesn't matter anything. I am going to wait for the seek time, also the rotation time anyway. For the sequential files, of course, this is a problem. That's called the skew amount. Another optimization that we can do with the disk formatting is interleaving, and we talk about that. The interleaving is simply this, okay? There is no interleave in this case. Sectors are 0, 1, 2, 3, 4, 5, 6, 7. But the problem is this. For a sequential file, when you read the sector number 0, okay, right after that, you need to read sector number 1, then 2. But the thing is that, remember our sector structure. This is our data. At the beginning, I have the preamble, I have the data, then I have the error check, right? You read your data, you calculate the checksum number, and you compare it with this one. If it is okay, if it is the same, then you are fine. You are ready to read your next sector. If it is not, there is an error. But in the case that there is no error, there is no problem, then I can start reading the next one. But the thing is that reading this and calculating the checksum takes some time. While I'm calculating the checksum, my disk rotates, and I miss the sector number 1 while I am calculating that checksum. So they say that, why don't we do this then? Okay, sector number 0 is here. I read it. I am calculating the checksum. I am ready. I said that, okay, checksum is okay. I am ready to read my sector number 1. And by that time, my disk rotated a little bit. Now I am reading sector number 1 and sector number 2. So this is a single interleaving case, and if it is not enough, then I can use the double interleaving. So these are some of the optimization stuff that we can use for the disk. You may say, well, these are not valid for the case of solid state drives. Yeah, that's true. Well, again, I mean, in operating system world or computer world, these kind of problems keep coming back over and over again. Maybe we don't use disks on our personal computers, not that much, especially for our mobile computers, laptops. But for desktops, still they are. I mean, I never heard of 4 terabytes of SSD storage. Maybe there is, but they are too expensive. Or we don't use SSD storage for the network drives. Okay, so they are still being used. So we are looking at them. Okay, these kind of details are the reason why the I/O part of the operating system is so complicated, so crowded. What did I say? Most of the code that goes into the operating system is due to the input-output stuff for the peripherals, because they are so detailed. I mean, disks have their own problems, their own optimization techniques. What else? The network drives, they have different USB drives, they have different stuff. Our graphics cards, they have their own problems, and somebody has to deal with it. Most of the time, these are all problems of the operating system. Okay. Okay, let's move on. Another optimization with the disk is the disk arm scheduling algorithms. Okay. So far, our optimization, our procedures were very simplistic, very simplistic. Somebody said that, okay. Somebody said that I need the sector number 12 from the track number 2. Okay, sector 12, track 2. Okay, that's fine. I will go there. I will make a seek, then they wait for the rotation, then I access it. But usually we don't work it this way, okay, because we have multi tasking operating systems. We have lots of requests. One user says that give me the block number 512. The same user at the same time says I need also 216, 730. Another user says that I need this one, and the operating system needs 175. Okay, because everybody is using the desk. So our driver for the desk device needs to get these blocks, okay, from the desk. I cannot share the desk in a time sharing fashion. I have to order them. So what is the order of accessing these blocks in my desk? Okay, first come, first served is the first thing that I can do, which would be the simplest, and you might say that it is the fairest, but it turns out that it is not that good, because, I mean, if remember with the desk, the seek time is the most time consuming step of the whole process. I don't want to do the seek time many times, okay? So what do? Maybe I should get all the data on the same track, then I should move my read-write head after that. So address all the track related addressings first, later move your head and read those tracks, move your head, read the other tracks again. So the smart thing would be, which ones, okay, this is track number 1, track number 7, track number 8, and track number 1, and track number 7. So it makes sense to read these two first, because they are in the same track, and maybe these two, and maybe that then, okay? So make these kind of optimizations. This makes it not first come, first served, but some other ordering. Other thing is, which track should I move first, okay? From after 1, should I go to 8 or 7, okay? That's called the problem of disk arm scheduling, okay? So we are trying to optimize this seek time. We like to minimize it, because that takes the most time out of this rotation delay, actual data transfer, and etc. So minimize it. So the first one is first come, first served. This is an example directly from the book. Let's say I have a desk with 40 tracks. So number of tracks is 40. And at the beginning, my head is at track number, maybe use a red one, a little bit better. Okay, track number 11. Okay, I am there. So these are the requests for the tracks. Somebody wants to read the data from track number 1. Okay, if you have multiple platters, we have many tracks, and we call them cylinders. Then 36 and 16 and 34 and 9 and 12. Okay, if I do first one first served, that would be the case. Okay, so from 11 to 1, I need to move my read-write head 10 cylinders. Okay, then from 1 to 36, I need to move 35 cylinders. Then from 36 to 16 is going to take 20. Then 16 to 34 is going to take 18, and 25, etc. So it will be 10, 35, 20, 18, 25, 3, and total of 111 cylinders. If my if my cylinder to cylinder head movement time is, let's say, 5 milliseconds, because these are expensive stuff, it's going to take more than 500 milliseconds. That's a lot of time. just to meet this first come first serve policy criteria. Okay, maybe we can do it in a smarter way. Smarter way would be, okay, this is the read write head, how it is moving from, okay, no, I think this is the next algorithm. This is how it is moving. This is like, if I do it this way, not that way, if this is 0 and this is 39, at the beginning I am at 11, then I move to 1, then I move to 36 like crazy, just the other end, then I move back to 16, then I move back to 34. It's like zigzagging, right? My read write head is moving like crazy. So total of 111 cylinder movement. The next best thing maybe I can do is maybe get all these numbers. Don't do the first come first serve, but do the shortest seek first. Okay, I am at 11. These are the cylinders that I am going to reach, right? So the shortest one is of course this one. Go to 12 first, and after that shortest one is maybe 9, because 11 and 12 are so close. From 12 to 9, then after 9 maybe the closest one is what? It is 16, right? Go to 16, then maybe 1, then 34 and 36. It's going to be something like that. So this is shortest seek first. Well, it looks like how many cylinders I am traveling? Total of 61 cylinders. Not bad. It is like half of first come first served. But it looks like this is doing this zigzagging too, like back and forth, right? Maybe I can do better than that, better than this too. Okay, shortest seek first seemed logical at first, but looking at this picture, well, previously it was like this. It was like a first come first served. If I am not lucky, it's going to be like this and this and this and this and this, right? That's why it was taking 111. Now we are down to 61. But it looks like I wish instead of doing this zigzagging, I do these two together and these two together maybe, right? That would have been better. So first come first serve is shortest seek first is another algorithm that you can follow, but we can do better. The other one is the elevator algorithm. Elevator algorithm does this. It says that my read write head is either going this way or this way. I don't change directions until I hit the end of my cylinder range. This is what they follow with the very tall building elevators. Let's say I have a building of 100 floors. Okay, very tall building. Okay, I have 100 floors and I have an elevator. Okay, and everybody can hit the elevator call button at their floors. So those are kind of my seek requests. Okay, the elevator algorithm that they implement is kind of, my elevator goes this way, and when it is on, it goes down, then it goes up and it goes down. While it is doing it, if there is a customer waiting, I can stop here, then stop here, then stop there, then go up. Okay, this is the elevator algorithm. So when I started at 11 and I am going up, then I come to 12, then 16, then 34, then 36, then I come down to this one and that one. So it is total of 60 cylinders. In this case, just one cylinder better than the other one, but usually we prefer this algorithm. Of course, you shouldn't make your decision just based on single elevator algorithm result, but that's the case. Okay, so this is the discount scheduling algorithm that does the elevator algorithm. Any questions so far? Yes.
Are those those algorithms run on the disk controller itself?
Well, I mean, if I am talking about this in an operating system course, that means what? It's not a hardware related, it's a driver thing, right? But these controllers implement these algorithms in their hardware, in their hardwares. Remember, these controllers are very complicated, okay? What did I say before? Our disks nowadays, they are computers. They are running operating systems. They run Linux on them. They have multi-core CPUs on them, some of them. So controller means it's a computer. It is implementing it. But as a host computer, as the OS of the host computer, usually I assume that these are all implemented in the OS part of the driver. Okay, driver implements them, especially for the very early computers where these controllers are not that smart. Okay. Good. Any other questions? Okay, let me continue then. Error handling. For the disk, many things can go wrong, especially for the mechanical devices. Okay. And remember the picture that I showed you at the beginning of this chapter, maybe from 1980s to 2010s. Okay, our disk sizes they grew exponentially. We are our disk sizes are very, very large compared to those days, and the main reason is not the mechanical speed up. Well, there is a small mechanic. Well, there is a few times speed up in terms of mechanics, like the rotation speeds and the disk head movements and etc. But the main improvement came from the surface density. Okay, now we can store many more bits, millions of more bits for a given area on my disk surface. And that means what? If there is a smallest problem on my disk surface, I will lose lots of data. And this can happen from time to time because these are mechanical stuff. Sometimes some part of the desk. Okay, this is my desk. These are my tracks. And for some reason, I don't know what happened, but for some reason, let's say this area of the desk went bad. Okay, it doesn't hold information. Whatever I write to this part, I cannot get the same thing. Okay, I cannot get the same thing back. So this part needs to be I cannot throw away the whole disk. It is too expensive. Okay, and this is a very common thing. So this is called disk error handling. Usually I realize that this is not happening. Okay, usually I realize that this is not working during the low level formatting. Remember what I did with the low level formatting? I write some data. If I cannot read it back, then sector is a bad sector. It needs to be marked. And these are some of the stuff that we are doing. Okay, usually this is how the disk formats are done. For each cylinder, I reserve some spare sectors at the end of the tracks. After sector number 30 or 29, I keep 2 spare sectors. I don't keep any information in them. If I see that this sector is bad, sector number 7 is bad, during the low level formatting or later when I do the disk check, okay, I can do 2 things. One of them is this, okay, put sector number 7 in this one of these spare locations, okay, as simple as this, okay. Of course, this doesn't look very nice. Why? Because for a sequential read, after 6, I would expect a 7. 7 is not there, so I need to. So 7 is missing. What do? I need to wait until the rotation is complete for these replacement spare sectors, and I'm going to read 7 after that. Then I will come to this one. So that means what? For the sequential reads, I will get a penalty for the sequential read time. Or I can do this. I can put 7 in there and move everything 1 sector ahead. Of course, that means what? That means I need to push all the sectors, and that's going to be expensive when I am doing this modification. Either this or that. Okay, so this is how I do the error handling. So this happens so common, this happens so frequently that this manufacturers, disk driver software writers, they prefer wasting some space sectors at the end of each track. That's what happens. Okay, if the whole sector is bad, if the whole track is bad, okay, I cancel the whole track. I say that this part of the disk is bad. Okay, that's going to lower my usable portion of my disk a little bit, but it is better than throwing all the disk, the whole disk, physical disk, to trash. Maybe my disk is now 96% usable. This happens even with the brand new disk. When you format a brand new disk, mechanical disk, you will get a report saying that you have 3% bad sectors, 1% bad sectors, etc. During the lifetime of a disk, you would lose a few more percent, and that's how the disk completes its life. That's called error handling. And this kind of a thing happens with our SSD storages too. SSD storages, again, from time to time, for different reasons depending on the technology, some of the blocks, they go bad. So I mark those blocks and I never use them. But in SSD storage, I don't have the seek and rotation time, so it doesn't matter where I keep my spare sectors. They don't have to be sequential. They can be anywhere on the SSD storage. Their optimizations are different. Okay, so this is just one case of handling the errors. Any questions so far? Okay, if there are no questions, let me continue. Then remember the RAID systems, we like them so much because using more than one disk, I can get both speed and reliability, right? I mean, if I am using 8 disks to store my data, I can get 8 times more read-write speed, okay, sometimes at the upper end. And if one of the disks go bad, then I can recover my information from the other 7 at the expense of keeping some redundant checksum data. Okay, that was a nice part about the RAID system. But there is a problem with the RAID system. It is this: while I am writing some data to the disk, if my operating system crashes, if the disk crashes, then my disk will be in an unstable situation. For example, remember our inodes. To keep a data on a Unix system, I need to reserve some inodes, okay? I need to modify them. Also, I need to modify my disk block for my data. If, while I am doing this, if something goes wrong, either I am going to have my inode state in an unstable situation, or my file data will be bad. So that's going to be good. So for that, they invented this stable storage idea. Stable storage, in the simplest case, it uses a pair of identical disks, okay? And I keep exactly the same data on these 2 disks, okay? And this number 1 and this number 2, okay? So when I am writing my data, I write the same data to this number 1 and this number 2. When I am reading from my data, I can read either number 1 or number 2, okay? Or I can read from both, so it makes it like a RAID kind of approach. It makes it faster. But the idea of stable storage is not for the speed, it is for the stability. Let's say before I write any data, let's say somebody told me that remove this directory from the Unix operating system. Before I did anything on my desk, my system crashed. So my disk number 1 and my disk number 2 is in stable condition because I did not change anything. Okay, I am not that lucky. Let's say my computer crashed while I am while I am modifying this number one. So in that case, okay, my operating system knows that my disk regarding my directory, okay, the disk number one is not stable. I started modifying it before everything is done. It has crashed, so I need to get all of my data from the old disk to the disk number one. So I have this all the information in stable form, and I can get this one to this one. So my situation is at the beginning of remove this directory kind of thing. If the crash happens between these two, then I have both new and old. Depending on my preferences, I think I would just copy this new one to the old one. Or if I do this, I have the new one, this has crashed. I know what happened. If the crash happened here, then there is no problem. This is called stable storage, and the motivation for stable storage is always have some kind of a stable representation of your data, valid data, in either disk number one or disk number two. Of course, my disk number one and disk number two, they could be both different RAID systems, right? They don't have to be a single disk. So I can get both speed and the stability out of this picture. Okay? As I said before, for reading, I can read two disks at the same time. One part of the data from this number one and the other one from this number two, and that would make it faster. But for writing, there is no speed efficiency because I need to keep exactly the same data on two of the disks, so I need to spend the same time. Okay, good. Any questions? Let me move on then. We talked about this, and let's talk about this clock hardware. We always, we many times talk about our clock device, okay, timer device, but we didn't talk much about this driver. It's a device, right? Since it's a device, we usually refer to them as I/O devices. Clock is kind of a special device. I don't want to call it I/O device, but other than the I/O devices, we don't have any other devices on our computer system. So let's talk about clock like an I/O device. What is the responsibility of the clock hardware? Creating interrupts. That's the responsibility. Somebody programs it. It says that give me an interrupt at this intervals, or give me an interrupt after this many microseconds, or give me an interrupt exactly at this time, and etc. And it produces an interrupt. And of course, the operating system handles it. And as regular end users, programmers, we never talk about interrupts. We never talk about clock hardware. Usually, we don't have any idea about this. But usually, when we have C functions like sleep 1000 milliseconds, that means what? Make a system call, program the timer, system timer for 1000 milliseconds. After 1000 milliseconds, the hardware will produce an interrupt, and that interrupt will be handled operating system. And while that interrupt is being handled, operating system will unblock my process. Okay, so until this happens, I am on a blocked list. Okay, not ready list, but on the blocked list. Okay, so let's look at this clock hardware. At the beginning, they have implemented this clock hardware by looking at the main power of the computer. It is either 110 volts or 220 volts, right? Power line. And we know that our power lines, they are not direct current, but alternating current, right? So either 60 hertz or 50 hertz, okay? 60 times a second in our country, we get these peaks, and at each peak, the clock hardware says that at each peak I am going to produce an interrupt. Okay, that will be our timer interrupts, timer ticks. Okay, that was this at the beginning. Later we didn't like it because this is not programmable. If I like to have a timer interrupt every 30 milliseconds or 40 milliseconds or whatever, I cannot use this anymore. Okay, and for computers like this one, this doesn't use the alternating current. This uses a direct current directly, so this will not work. So what did they do? They use this technology of oscillating crystal oscillator. Okay, that's the quartz oscillator. Quartz works this way. That's the basic thing about the digital clocks. Okay, there is a special material, it's called quartz. Okay, if you put some pressure on this quartz material, okay, this one, quartz crystal, if you put some pressure on this quartz crystal, and if you apply some current to it, at very precise intervals, it produces a signal like that one, like a peak. It's the nature of it. Okay, it's some kind of a nice invention. You apply some pressure to it, and you apply under that pressure, you apply some current. Okay, it takes this current, let's say after every 2 milliseconds or after every 1 microseconds, it produces a peak signal like this. Okay, so this crystal produces this, and I get this signal, and I use the signal to decrement a counter. Let's say I think this is 16. This is 16-bit counter. Okay, if it is all ones at the beginning, okay, let's say if it's all ones, when this happened, I decremented it by one. It happened again. Now I decremented it by 1 again. This is 0, 1. And it happened, and I decremented it again. And it happened. Now this is 0. You get the idea. So if it is happening, okay, 1 microseconds or 1 nanoseconds intervals, okay, this 16-bit number will get smaller and smaller and smaller. When this number hits 0, okay, my hardware produces an interrupt. So it's basically a counter. When the counter hits 0, it produces an interrupt. Okay, after the interrupt is produced, this number here is transferred to this counter again, and this whole process again starts from the beginning. This one doesn't have to be all ones. For example, if I like my interrupts in a smaller, if I like to have my interrupts in more frequent way, then make this number smaller like this, or even just put some zeros at the beginning. Now you are going to get more frequent interrupts, timer interrupts, right? So every time this number reaches 0, I produce an interrupt, and I move this data to this case, to this place, this counter, and it will go that way. Okay, this is the whole thing about clock hardware. I did not talk about any driver part of it yet. I told you how the hardware works, right? So without understanding the hardware a little bit, of course it is difficult to talk about the driver. Let's talk about the driver now. Okay, none of the stuff I talk about in this slide implemented in software. They are all in hardware, and it's very simple hardware. The important thing is this crystal oscillator. And when you say I have a computer that runs at 2.4 gigahertz, that means your crystal oscillator is producing 2.4 giga pulses, okay, per second. Okay, that's how the crystal oscillator works for your CPU. Your interrupt crystal oscillator doesn't have to be this fast, okay? It could be a little bit different, okay? It is a little bit slower. Making this fast for your interrupt for the clock hardware is not that meaningful, but that's the meaning of it, okay? That's the meaning of this crystal oscillator running at this rate. Okay, so the clock software, the clock driver, we use it for many purposes. For example, the time of day, maintaining time of day and date is very important for us. I like to know what time this file is created, modified, read, and etc. Okay, that's one thing. The other thing is, when we are doing the process scheduling, thread scheduling, we like to be fair between the processes. If we are using preemption, I don't want any users to use the CPU more than 50 milliseconds. Okay, so I program my timer hardware so that it produces an interrupt every 50 milliseconds. I handle that interrupt and I switch from process to process if the process doesn't voluntarily give up the CPU. Accounting for CPU usage, somebody has to calculate how much CPU each process has used. Usually my processes, they don't use their quantum time, remember? Before the timer happens, usually they they make a system call. I need this data. I need to write this to the screen and etc. So it is not that easy to calculate how much CPU my process has used. So I use that. I use the timer hardware and drivers to do this accounting for the CPU usage. Handling alarm system call from user processes. What did I say before? Sleep 1000 means that I'm going to be blocked voluntarily for 100 microseconds, milliseconds, and wake me up, or produce me a timer at this exact time, etc. Watchdog timers, we'll talk about it. These are very useful for, especially for the embedded systems. Other than that, profiling, monitoring, and statistics. For some operating systems, for example, if the operating system is giving me this kind of information, about my processes, my CPU time for the whole processes like this, okay, for a very long time, that means that I am profiling something. I keep this information, not for the processes, maybe for the threads too. Okay, so these are the things that I use with the clock software. Let's look at them one by one, or maybe before that. Do I have time? Yeah, let's look at them one by one. After that, I am going to talk more about how this whole timer stuff works, how I program it, how it handles all of this kind of stuff at the same time. But I think I need to take some break. Any questions before the break? Where is the attendance sheet? Did everybody sign it? Can I have my attendance sheet? Okay, let's take 15 minutes of break. Let's be here around 11:30. Dün bana 50 tane mail ulaştı. Hangisini sileyim? Notlara bakarsınız dersin.
Tamamdır hocam. Teşekkürler. Tamam anladım. O zaman iç içe bir ilk boyutu mu? Ama bütününü anlamaya çalışıyorum. Sadece tam şu an çalışması var ya.
Ya bir şey var, task'ın var, onu ayarlamaya çalışıyorum.
Bitmedi. Hala 2 gün dedin. Son gün mü bu? Onu hazırlayalım oğlum. Ne son? Sen oğlum çalış. Olsun abi hiç bakmadın değil mi? Güzel. Acaba şu ertelesi hazır var ya. Rapor için en azından. Sen de haklısın. Aynısını yapıyorsun. İşte ertelesin kanka. Aynısını daha rahat göndeririz. Evet. Orası öyle. Perşembe, cuma yapması daha farklı.
Şöyle.
Ya ne olacak? Gönderdi online olsun. Mustafa'lara soruyorum.
Herkesten gidiyor. Tamam, çok iyi abi. Sıkıntı yok.
Kalırız yani. Belçika'ya gidiyoruz. Sene veririz de 6-5'ten 10 gerekiyor oğlum. Proje dersinde de proje dersi de var ya. 30 haftası 10 bin dolar. Bir hafta kesin. Verir ama. Ama o ortalama 3 lira düşer o zaman. Alamaz. Büyük ihtimalle. Değil mi abi böyle nasıl?
Ders ekstrem istedim.
İstemesinden yani şey yiyebilirsiniz. Biz yemeyiz de. Ben desem data ödevi var. Der ki ne yani geçen sene geçseydim. Ama siz deseniz ki data var. İhtiyaç alıyoruz.
İlk seneye alacağız. Ben
Neyi? Datayı? Ama şu an 4. sınıf çok var. 2. sınıf yoktur. Anladın mı? Çünkü sınıfın yarısının datası var. Bak senin var, Mustafa var. Bu tayfanın da komple var galiba. Değil mi? Dermişler,
Dermişler almıyor ya.
Dermişler ama Enisler alıyor. Var.
Enis alıyor, ben alıyorum, Oğuz alıyor.
O tayfa alıyordu. 3-5 kişi. Yani data alanlar çok var.
Diyorsun ki deneyelim.
data alan çok var da. Yani ben de alıyorum da çok fazla.
Aynen data alandan çok vardı. Database alanı.
Tamam ben de database alıyorum da çok fazla takacağını düşünmüyorum hocam.
Zaten 2 gün falan daha fazla erteleyecek. Bir hafta ertesinde mi? Raporu rahat eder.
Yani denenebilir.
Çarşambaya bir tane ya da sallayacağız. Yaptın mı öyle?
Yok ya ben şeyde takıldım. Block size'da o block size olaylarını anlamaya çalışıyorum da 4 KB verdiğinde işte 8 KB verdiğinde falan. Onları dinamik yapınca kapıyor ya.
Bitmap'le kontrol edeceğim.
Bitmedi.
Freelist de gerekiyor da bitmap'le yapınca ne oluyor çok fazla.
Bitmekten kastım ne tam
İşte
olarak?
boşlukta olur mu abi? Sen neyine tam şey yapmadın?
Mesela block structure block diye bir şey oluşturup içinde.
Hayır öyle değil. Memorideki bloğu temsil ediyor.
Okey.
Yani bir blok kaç kilobayt olacak?
Tamam memorideki bloğa nasıl?
Dosya direkt memori. Memori dediğim şey hafıza yani.
Olmazsa olsun.
Dosya var ya 16 megabayt. Onun bilmem kaçıncı adresinden, bilmem kaçıncı adresinden adres dediğimde işte 16 megabaytın İşte 14. megabayt, 16. megabaytına kadar mesela dosya var farz etmekten. O dosyalar senin o verdiğin kaç kilobayt blokları halinde olacak diyor. Yani 14, 14.4 kilobayt, 14.8 kilobayt şeklinde ilerletiyor. Tam öyle olmuyor da salladım şimdi. Kilobayt olarak yazınca daha düşük oluyor. Sıkıntı o değil, sıkıntı read write'lar falan çok karışmıyoruz.
Değiştiremedik.
Çünkü işlemin ne olduğu anlaşılmıyor. İyice, SC, İ, isimlendirmeler 10 numara yani.
Abi böyle program olur ya.
SQL'lerden mi buldunuz?
Aynen.
Bir bakımlık konuları da anlaşılmıyor şu.
Ben de baktım da birkaç tane çok şey ya, çok şey, özel şeyler yani çok önemli
Kendi
şeyler.
alıyor.
Değiştireceğiz ya biraz.
Eki APK mı yaptın?
Evet,
Güzel mi?
APK yapatacağım.
Sen anlattın mı yoksa sallayacağım mı? Çok güzel. Kablo olsun oraya.
Mustafa'ya tak. Sen şey yaparsın. Yani ne yazdın kabloyu? Şey yapıp beraber. Aslında daha hafif.
Nasıl yapmamız lazım? Data var, datanın projesi var. İşte nereden vereceğim?
Dataya beraber bakarız. O da beraber bakarız.
Datanın zaten kitapçılığı var, kodluğu var.
Direkt yapıştırma.
Onların işte çevirmemiz gereken kısımlar olabilir. Yani azıcık manipülasyon istiyor.
Bakarız ya.
Yoksa zaten Murat Hoca çalışan falan yapmak gibi bir şey.
Murat Hoca bakarız.
Kodlu çalışıyorsa ben
Doğru çalışıyor diye bakarız.
SS'lere bak.
Evet. Bunlar genel rapor alır. Sen de dataya alır. Sonra sistem yapıyor. Ona göre.
Sistem hallederiz çok bak bence.
Bence de.
Çok aşırı karışık bir şey veremeyecek. Çünkü kimse geçemiyor yani. 12'yi geçeceğiz zaten.
Database projesi var. Ona da bir 50'lik kalacak bir şey yapacağım. Database.
Karışık bir şey mi oldu yani? İçsel cerildi falan mı?
İkisi de ben de yani rapor yazmışım.
Raporcu zaten
Acemiyiz ya bu işler. Arada bir tane yaptıklarımız çıkıyor.
Yaptınız mı dedim.
Yok ya daha başlamadım.
Evet bugün.
Ne?
Evet bugün.
Sen ne yaptın mı?
Ben de başladım.
Bir tane gözü kesiyor.
Kesiyor yani. Geçmesine diye yazıyor ya.
Öyle mi?
Ha, oradan öyle.
Üç part, üçünü de yetiştiririz o zaman.
Ben üçüncü part 3 salacağım ya. Part 1 part 2. Ama zaten part 1'de part 3'e mi aldım?
Part zaten şey parti yok yani parti rapor zaten.
Kolay mı peki? Değil. Kolay değil. Part 3 salıp yaparsan herhalde olur. Yani yeterli burası için. Kaç? 40. Tamam 40 saat. Ben şey istiyorum.
Minimum düzeyde.
Belli olsun bizim olsun.
Aynen.
Çıkış yapmamışlar şöyle.
Kantin kapalı.
Kantin kapalı mı?
Şey dedim olsun mu?
Ha.
Yapmadın mı? Artıyor kantin sayısı. Biraz
Gidiyor. Sonsuza gidiyor abi de böyle. Ya ne yapayım ya? Bunaldım artık abi.
Canımız sağ olsun abi.
Vallahi bunaldık artık.
Verse dönem içinde okey mi şimdi?
Ben görmüyorum.
Efe olsun. İyi de bir sonraki dönem Yok, buna sıkıntısı olmaz. Pişmanım.
Hallettiniz mi projeyi?
Biraz müzik attık.
Şey,
Uygulama mı yazdınız sadece?
O da var. Windows App'te var.
Makine öğrenmesi falan.
O da oluyor.
ama bugün olayı yapalım. Biz verileri aldık böyle tam yolluyoruz abi.
Kaç kişiden test aldınız?
Sıfır.
Hallettiniz mi?
Bugün halledeceğiz inşallah.
Kanka random'a koyuyorsun.
Aynen.
Aynen öyle.
Öyle bir şey.
Ve bir tane alırız. Randomla aralık atarız. Değiştiririz. Kendi kendine bu kadar önemli.
Kendi self learning değil mi?
Aynen öyle.
Benim testimi de kendi aldım.
Kodla söylesin.
Ha tamam. Bak sen yapmadın.
Ya.
Çok iyi oldu.
Ha? Ne yapıyordun?
Olmadı mı olmaz. Ne yapalım?
Benden değil şimdi. Durur mu?
Şu
Anladım yer dedim abi. Şöyle ben onları aldım.
sıkıntı yani.
Almayı bir self learning.
Selfie yapmaya
O da saçma ya. Bir yapsa
O şey, olasılık alıyor mu? 13'üne bitiyor yazdım.
Allah'tan sorun yok. Ortalar 7'sine falan atmaz.
Var ya.
Tam böyle patlar.
Ne işte? Aynı şeyi öğrendik. Daha doğrusu aynı anda.
Biliyorum ya, alet çalışmasında ikisinde de alet kuşağı çok güzel bir zararlı malzeme Yok ya ben
Çok kanka.
Hocam ne yapacağız projede ya? Ya valla bugün bir şeyler yapıp işlemeye çalışıyoruz.
bana
Proje bilmiyorum ya. Ya bırakmak gerekiyor. Sahnesinden tutuyor bak sahnesinden tutuyor.
Okay, so these, let's look at these clock. Let's look at these clock software responsibilities one by one, some of them at least. Maintaining time of the day is something that we need to do. How do we do this? Okay, starting from a known time, we just count the number of ticks. If I am producing 60 interrupts per second, okay, then that means that after I reach the count of 60, I know that a second elapsed, and I can mark this with a number like the 64-bit number, very large number, and basically I am counting the number of ticks after a known time. And you might say that this is overkill. Then maybe I can do this. I can count the number of seconds in a day, plus I can count the number of ticks in a current second. If this one reaches, let's say 50, I increment this one. And another approach would be system boot time. I take the system boot time from a time server or maybe an auxiliary time device, and I count the number of ticks using that way. So these are some of the assumptions to keep the time of the day. Similar assumptions are made for keeping the date of the computer. In 1980s, they assumed that whatever we are using, whatever we are building, they are only temporary. So they assumed that most of the software in 1980s, they assumed that it is okay to have two digits, digit number 1 for the day, okay, D1, D2, month 1 and month 2. This is, okay, 2 digits for the day, 2 digits for the month, and 2 digits for the year. So like 81, 82, 83, 84, etc. They have never realized that we will keep using that software until 2000. Okay, when the year 2000 came, after 99, it will be 00. That means what? The files that are created in 2000 will be older than files created in 99, and that's going to cause lots of system crashes. And they call this problem year 2K problem. Okay, and in 2000, before 2000, they were expecting that many computers will crash, and most importantly, many nuclear power plant controller computers will crash, and we will have a nuclear catastrophe. And everybody was running around. People spent literally billions of dollars to fix these problems, Y2K problems. And year 2000 came, and nothing much happened actually. No computers crashed because they spent lots of money on it. So the thing I am trying to say is that don't make these kind of assumptions that the software you are developing is going to be obsolete in 2 or 3 years. It will not be in use in 5 years. You will never know. It might be used for 200 years, not on your computer that you are developing, but your software, because your software is transferable, yeah, right? I mean, the many software that we use today are developed on maybe 20-year-old computers, but still we are using that software. Okay, I mean, most of the embedded systems, they use this FAT16 file system, right? Which was developed in 1980s. Okay, so whatever decision that they made in those days, we have to carry on with those decisions. Okay, and some of these decisions are made a long time ago, and sometimes they create problems because after 2032, many Unix systems will have problems because they will not have enough tick counters after. I think Unix time starts from 1970. Okay, they have never realized that this system will be in use in 2020 or 2030. That was like, we had developed this in 2 years, 3 years, and remember how they developed Unix? They say that Multics, let's have some fun. It's not Multics, but it is Unix. So let's develop it because this computer is sitting idle here. Let's have some fun. So that fun turned out to be a very useful thing, and we are still keep using it, and it looks like there is no end to it either. It looks like we will keep using it. Mac OS is based on Unix. Windows is trying to be compatible with Unix, and it's going to be based on Unix, and it will go that way. Okay, so that's how we keep the time of the day. The other one is this one. Preventing processes from running longer. Okay, preemption. Okay, every clock interrupt. Okay, preventing. Whenever the process is started, the scheduler says that I am going to give you this many timer ticks. Okay, if my timer is happening 30 times a second, I am going to give you 4 timer ticks. That means that after 4 timer ticks, I am going to stop you. So at every clock interrupt, the clock driver decrements the quantum counter by 1, and when it gets to 0, the clock driver calls the scheduler to set up another process. So the clock driver is communicating with the other parts of the operating system, of course. It says that you programmed me, you told me that give you a call when this happens. This happened, I am going to give you a call. Okay. So, but it is done using this case. Other stuff, accounting for CPU usage. Okay. I like to know how much CPU I have used for this process. Okay. You can do this. You have a counter in your process table. Okay. And that counter is decremented or incremented whenever a timer interrupt is happened. Okay. So there is only one counter currently active. When the process switch happens, you switch your counter to that counter, and your clock software increments that counter in your process table whenever a timer interrupt happens. Okay, this is a one way of charging your process table about the CPU usage time. The other one could be more precise. You note the beginning of the process start time, the switch time, end of it. You make a subtraction between those. It might be a little bit costly. Okay, so clock software is responsible for accounting for CPU usage. We already talked about that. The other thing, maybe one of the most frequently used parts of the clock is the alarm system calls. Okay, in Unix you can set up alarms, right? Wake me up in 50 milliseconds on do this and that, etc. Okay, or I am running, give me an alarm when this many seconds has passed. Okay, for example, in network we do this all the time. This is our network. Let me show it this way. Internet cloud. I am connected to this, and I'm connected to this. I am sending a package from here to this computer, and sending these packages takes time. When I send a package, okay, I keep sending it, and somebody has to inform me that after I send the package, for example, after 100 milliseconds, I need to check if I received the acknowledgement back. If I didn't get the acknowledgement back in 100 milliseconds, maybe I will try it again. Okay? So, in fact, I am not blocked. I am not waiting for anything. Okay? I keep working, but somebody has to remind me that it has been 100 milliseconds since you sent your package. You should check if you have your acknowledgement back. Acknowledgement is the other computer is telling me that I got your package. Okay? So, for these kind of cases, we need to set up alarms. Okay, I am telling the operating system that give me an alarm after 100 milliseconds to 100 milliseconds, and I can do this as many times as I like. Give me an alarm after 100, 200, 500, 150. This is my process. Many other processes might be doing the same thing. So the clock software is very busy keeping this data in mind, saying that I need to produce alarms for 20 processes. For different numbers, and I have to do this in an efficient way. Okay, in an efficient way. You might say that let's program the clock hardware so that it produces an alarm at this time and that time and that time. That might be a solution, but that would be too inefficient, because interrupts means that somebody has to handle it. That means context switching. Context switching is expensive. Okay. We don't want to produce an interrupt, hardware interrupt, for all of these tasks, and we need to be a little bit smarter about this problem. Okay, so this is how we actually handle all that stuff. Okay, my clock software, my clock driver keeps this information. I have my current time. Let's say this is the number of clock ticks. Okay. It has been 4,200 clock ticks. Okay. My next signal that I am going to produce is in 3 clock ticks. And after that, the next signal will be 4 clock ticks later, then 6, then 2. It is like this actually. Somebody said that wake me up at this 4203, 4207, 4213, 4215, and 4216. I have 1, 2, 3, 4, 5 waiting clock jobs that I need to handle and I need to wait. Okay? My current time net signal is this. Every time, okay, every time a clock interrupt happens, I decrement it by 1. I decrement it by 1. When this one reaches 0, that means that I need to wake this up, whoever is waiting for this one, and take this out from the queue and put this 4 in here, and now decrement this one by 1. Whenever a new request comes in, I scan this list and I place that request in the linked list, and I wait. I keep making this work. Okay. So this is a very basic data structure, a linked list sorted with respect to the wake up time, and I don't keep these numbers like 4207 or 4216. I keep it like this. Okay, how many clock ticks after this one I have to wait until I wake up this waiting customer? That's basically how it works. Basically how it works. Okay, good. That's the clock software. It is implemented. Very simple. We said that one of the things that we use the clocks for is the watchdog timers. Watchdog timers are processes, very simple processes. The process does that, okay? The process does this. How should I? Okay. The process does this. T gets the value of 1000 while T is greater than 0, T minus minus, and panic. The process just runs this one. It says that at the beginning my T is 1000, and I keep decrementing this value 1 by 1. When this value reaches 0, I tell the operating system that there is something bad happening. I am panicking. This is a watchdog timer. Okay? This is a watchdog timer. So what is the meaning of it? The thing is this. My other useful processes, for example, I have a process that, okay, very large process. You know the event-based programs, right? In the event-based programs, while there is a loop, okay, while one get event and handle event, right? That's the whole loop. That's how the event-based programming works. And we use this for mainly, in our case, if you remember it, for the graphical user interfaces. This computer basically, or the many interactive computers work this way. You get an event, you handle the event. If there is no event, it says that no event, and I handle no event, and etc. Infinite loop, it just works it that way, okay? You get the event, you handle the event. You get the event, you handle the event. After I handle the event, I just do this 1000. Okay? This T and this T are shared. Okay? So what's happening here is that while this loop is running, if it is alive, it keeps setting this T to 1000, and this watchdog timer keeps decrementing this value. If this loop works all the time, this watchdog timer will never go off and will never panic, right? it will keep decrementing this t value because somebody is setting this to 1000 all the time. Okay, but if this event-based loop is dead for some reason, it is crashed, my screen is not active anymore, so I have to panic, and operating system has a way of saying that, okay, my event-based loop must have crashed, so what should I do? I start it again. Okay, I start it again. That's why some part of our operating systems are very robust. Even they crashed, even if I crash it on purpose, for example, if I go to my task manager and if I kill, for example, performance processes, for example, if I kill one of the desktop stuff, where is my desktop? Yeah, see, this was, I cannot keep it. Let me short it to, okay. Masaüstü. Do you see it? Where is it? Do you see my maybe this one?
Explore that.
Do you see my masaüstü? Well, whatever. There must be a desktop manager. If I kill that desktop manager, I won't be able to move my windows, or all of my windows will lose their handles and everything. My system is not interactable now, but some watchdog timer will realize it, and they will tell the operating system that your desktop manager is not working. So operating system will start another desktop manager, and I can do this for the file drivers, and I can do this for operating system schedule and different parts of the operating system. And these watchdog timers are actually they work this way. I simplified it very in a very crude way, but usually these watchdog timers, they don't run in this kind of a loop. Okay, every timer happens, you decrement this t value by 1. Okay, and after that you check if the t is becoming 0 or not. If it's 0, then something bad happened and something has to be done. Okay, this is very valuable for the embedded systems, because with the embedded systems, nobody is going to boot your computer for you. Okay, what's an embedded system? This is an embedded system, right here. If camera crashes, how am I gonna restart it from as an end user? It doesn't have a button. It just, sometimes I lose a few frames, okay, but it starts it again, and the computer doesn't know that it has restarted. It just thinks that something bad happened, software related happened. Or your, for example, simple music player on your ears, right? Sometimes it just glitches, doesn't give you a right sound, but after a second it starts playing it again. These are all caused by the watchdog timers. Okay, watchdog timers. Good. So what else? We talked about this. So let's look at the cost of the timer stuff. We like the timers. They are based on the interrupts, but interrupts are very expensive. For all the tasks that I mentioned about, 4 or 5 tasks, each one is talking about, let's get an interrupt, after the interrupt this happens and etc. No, I don't want to have that many interrupts. Okay, that's too much. So what do? Maybe I should do this. The processes are interrupted anyway when there is a, for example, system call, right? When there is a system call, the process is interrupted, and because the operating system is running, context switch has already happened. If the context switch has happened, okay, I just check this linked list to see if any of the waiting timers are close to expire. If they have already expired or they are very close to expire, I say that I am going to handle this one. Although I did not meet the exact time of the timer, okay? I say that it is good enough, it is approximate enough. While I did the context switching, okay, I am going to handle this case or that case, etc. These are called soft timers. That has the name soft. It is not exact time, okay? It is not exact time. It is about the time of the interrupt that are desired. If I handle many interrupts at the same time when the context switch happened, I will save lots of context switching time, and that will make my overall timer handling and operating system very, very efficient. Okay, so soft timers, they will try to avoid the interrupts, and they try to make use of already happening interrupts, like the system calls or the cache misses or the page replacement stuff. And when it happened, I handle as many timers as possible. Of course, the downside is I am not going to handle those exactly at the same time desired, but most of the time these are all okay. I mean, when I say I am going to sleep for 1,000 milliseconds, do I mean that exact 1,000 milliseconds? No, I am saying about 1,000 milliseconds, right? Or if my package is not back in 50 milliseconds, 49 milliseconds or 51 milliseconds is okay. That's called the soft timers. And soft timers will run when there is a system call or TLB miss or page faults or I/O interrupts and etc. So the basic idea is this. Okay, being 10 microseconds late from time to time is often better than having your interrupts eating up to 35% of your CPU. Okay, we are kind of trading efficiency with a little bit sloppiness in terms of handling the timers on exact time. Okay, again, timers are important. Timers are hardware components, and there has to be a timer driver. They are very involved with the rest of the operating system, and we have to talk about it, of course. And there are many things that you can make your overall system efficient using your timer drivers. Any questions about the timers? The rest of this chapter is about your other I/O devices like your keyboard, your mouse, your screen, and etc. I don't want to spend much time on it. You read your book. I am not saying that these are not important. Of course they are important. But basically, I mean, your keyboard causes interrupts. It causes, every time you press a button and you release your finger, it causes two interrupts. One for the button press, the other one is for the button release. And your operating system handles those buttons, okay? And your keyboard driver makes sense of these buttons. It says that button number 13 is pressed. What is button number 13? On a Turkish keyboard, it is Q, okay? But what is my keyboard state? Well, in keyboard state, it is your caps lock is on, your function button is on, so it must mean that. So these kind of things are decided by your driver, and on top of it, you have your I/O libraries. So your interrupt handler, okay, which is the keyboard interrupt handler, on top of your system I/O software, on top of it, your I/O libraries will make sense of these kind of interrupts. Those are for the keyboards. For the keyboards, the interrupts can happen maybe at most 10 times a second, not much. Okay. Okay. Mouse is the same thing. Mouse interrupts are more frequent because for the mouse, many more things can happen. When I scroll my mouse, okay, it causes an interrupt, maybe 50 times a second. It says that I have a movement of the mouse in X and Y directions, this much. Also, I have left button click, right button click, middle button click, or double click, or single press, or drag, or that kind of stuff. These are all handled by the mouse drivers. Okay. And then you have your output stuff. What am I going to print to the screen? Of course, those are all windowing based stuff for nowadays. It is detailed, not very complicated, but detailed. And usually we follow what they have set in 1980s at MIT X Windows system. Okay, for the Unix, they have developed this X Windows system, which is the windowing system that we use most of the time. Windows is kind of modeled after it. Apple operating system is, of course, a Unix system. It says that okay, your screen is actually, whatever you are seeing is like a server. Your programs that are using these servers are your clients, and your client and server doesn't have to be on the same machine. So your server that draws on the screen is completely, might be a different machine, and they can communicate over a network such as TCP/IP network. Okay, so remember our network-based operating systems, just kind of an example for that one. So Unix said that this is too modular to make it part of the operating system. So the Unix keeps all these screen management stuff out of the kernel. Windows doesn't do that. It makes it less, it make it more efficient. Our machines are not as powerful as those. Okay, so that's the difference. And I think we have a simple X window application in C. Your display your window graphics context events. Okay, see, this one is, it is getting an event and it is handling the event-based programming. This is your main event loop. When this loop is broken, then you break up everything. Okay, so you used to, in 1980s, you used to write your event-based loops. It is not like Java kind of stuff. You don't say just run. You have to write this loop. This is more flexible in terms of doing whatever you want, but it is difficult to write. Just to get a simple window like this, okay, you need to run hundreds of, well, this is complicated. Just to get a simple empty window, you need to write more than 100 lines of code like that one. Because each of these events, one of them is, for example, close button event. The other one is window resize. The other one is minimize, maximize, restore, etc. Okay, I guess I am not going to talk much about these either. Okay, graphical user interfaces. Fonts, okay, and other stuff are system resources, operating system resources for some systems. Again, these are becoming too much detail for us. I'm not going to talk about them much. You read the rest of the book in this chapter number 5. Okay, any questions about, that will be it about I/O. Any questions about I/O? Okay, for the rest of this lecture, let me talk a little bit about deadlocks. As I said many times before, I am against talking about deadlocks in operating system course, because nobody in modern operating systems, personal computer operating systems, nobody handles the deadlocks in the operating system level. If a deadlock happens, it happens. It causes a system hang up. If system is hang up, a watchdog timer will come in and will start something. Okay, at most I will crash, but a personal computer crashing is not a very uncommon news, right? We just restart our computer. Why are we doing this? Because detecting a deadlock and preventing it, avoiding it, and that kind of stuff, they are too expensive. If I am going to spend 20% of my CPU time to detect deadlocks, or if I am going to ask my end user that you cannot use your scanner and printer at the same time. Either you use your scanner or printer, not at the same time. If you are going to restrict your users to prevent your deadlocks, then I am against your deadlock prevention and everything. So either Unix or Windows or Apple operating system, they don't do anything about the deadlocks. So why are we talking about deadlocks? Because it is chapter number 6. Because if you talk to go to job interview and they will immediately start asking you about deadlocks, how do you prevent deadlocks and etc. These deadlocks are very easy to ask questions about, but they are not useful. It's like perfect operating system instructor chapter, very easy to ask questions, lots of details, lots of academical stuff. In practice, there is nothing in it. But I don't want to skip the whole thing. So look at deadlocks this way. They are not part of the operating systems. I am not saying that they are not important. Of course, deadlock prevention mechanisms and deadlock avoidance is very important for the databases. It happens a lot. For those kind of systems, it happens a lot. For networks, it happens a lot. But for operating systems, we just ignore them. So let's make an introduction to deadlocks. Okay. This is these are classical examples. Let's say I have a process A. This is Alice. Alice has taken the scanner. This is my scanner. Scanner is a resource. Process A took, the scanner. I locked it. I locked the mutex of the scanner. I have it. And then there is another process, Bob. Process Bob took the resource printer. I took it. This is how you take it. Process B took the printer. And Alice says that I need the printer, so I am going to scan a document and I'm going to print it later. And Bob says that I got the printer, but I need the scanner. I need the scanner, and this is how I request it. Typical deadlock. A has the scanner, B has the printer, and A needs the printer, B needs the scanner. And both of them are waiting for each other to release the resource, and they are going to wait until infinity. Nothing is going to happen. This is a typical deadlock situation. Neither can progress until the other does. And since computer systems are full of these kind of resources, and resources are limited, and we like to keep them. We like to, without locking the resource, you cannot use them, right? Without locking, there is an race problem, right? There is a race situation happening. I have to lock them, and that might cause some deadlocks. So the common examples of the resources are printers, tape drives, backup devices, or your records in a database. So these are the stuff. Studied a lot in early days of operating systems. Operating system theorists, not the practitioners, they love it. Why? Because mathematically it is very easy to draw these kind of graphs. This is a graph, right? Directional graph. And if I can detect a cycle like this, there is a deadlock, right? So you know the cycle detection algorithms in your algorithm classes or the data structures courses. So it's a perfect example to make use of your graph algorithm. But in practice, as I said, nobody uses them much. Nobody uses them much. But again, I need to talk about them because everybody thinks that deadlocks are important part of the operating system. Closely related to deadlock, there is a live lock. What's a live lock? There is deadlock and there is a live lock. Well, this is deadlock. There is an A missing here. Deadlock. Dead is a bad word. Lock is a bad word. So it makes a very bad word. Live is a good word, but lock is a bad word. That doesn't make this a kind of a better than deadlock. It's a lock. With the deadlocks, both processes are blocked. They are waiting for each other. For the live-like cases, they are both alive, okay, but they are locking each other. For example, this one. Think about this. Alice got the scanner, needs the printer. This is the case. Alice realized that it is not getting the printer, so it releases the scanner, and B releases the printer. After waiting for 5 seconds, Alice is doing the same thing. Get the scanner, try to access the printer. This one says, I'm going to get the printer and try to access the scanner. So they are trying to do the same thing at the same time. They are both alive. They are trying to do the same thing, and they realize that I am not getting it, so they give up. They try and they give up. They try and they give up. This is a live lock. They think that they are making progress because if I keep trying this, at the end I'm going to get it, but it's not happening because they are doing both the same thing. That's called live lock. Okay, so basically most of the operating systems, they ignore deadlocks and live locks. Okay, and I mean the thing is that we are not saying that they are not important. The thing is that they are expensive to detect. Okay, and they put lots of restrictions to the end users. Okay, so there is an unpleasant trade-off between convenience and correctness. Okay, so we choose the convenience side, and we say that okay, I'm going to take that hit. Okay, I'm going to crash 1% of the time, but I will be efficient and I will be convenient. Okay. Preemption is something that can be used to prevent deadlocks. For example, if process B needs the printer is not available. If I can preempt the printer, if I say that whoever is using the printer, just stop using it, and I'm going to take the printer, that will be a solution for a deadlock, right? But preempting the printer is a bad idea. Why? I am printing a 600-page document. I am at page number 200 and somebody is preempting me. So I need to start from the beginning. That's a waste of paper, right? So preempting the CPU is okay, because if I preempt it, whoever was using the CPU, they can start using the CPU again from where they left off. But preempting the printer or the scanner is not a good idea. So preemption sometimes works, sometimes doesn't. Okay? So preemptible and non-preemptible resources. CPU is preemptible. Network driver is preemptible maybe, but not the printer or the scanner. Okay. Another way to let's look at some deadlock situations. Here in this case, okay. Process 1, and in this case there is a deadlock free code, deadlock potential code. Potential deadlock doesn't mean that this deadlock will happen all the time. From time to time it will happen. Okay, let's look at this one, or let's look at this one. So I say that I need 2 resources. I get the resource number 1, mutex down. I get the resource number 2, mutex down. If I don't get this one or that one, I will be blocked, I know. This one says that get resource 2 and get resource 1. Okay, just do the opposite order. So if I do a context switch here, okay, and this one starts here, and when I come to this one, okay, this one will be blocked and this one will be blocked. In this unlucky case, there will be a deadlock. You might say that I can prevent this, just use it this way. If you get your resources in the same order, always 1 and 2, 1 and 2, right? Always 1 and 2. Then in that case, you can prevent your deadlock. So ordering your resources is one way to prevent your deadlocks. Order your resources. Always get your resources in the same order. But sometimes, especially for the databases, ordering is not that simple because you have many records. Ordering them and keeping that order will not be that easy. Okay, so these are the things that are needed. Very classical question. They will first ask you this: what are the necessary conditions for a deadlock to happen? Okay, it has to be mutual exclusion. I cannot share a printer. It has to be either process A or process B. Okay, without the mutual exclusion, there will be no deadlock. Okay, you won't be you won't be able to get a deadlock if there is no mutual exclusion. Okay, mutual exclusion has to be there. Second, hold and wait. There need to be cases where I am holding a resource and I'm waiting it. I hold the printer, I am waiting for the scanner. Okay, this may cause a deadlock. Hold and wait. No preemption. Again, for the CPU, I can always preempt. For the CPU, there will be no deadlock. But for the printer, there will be a deadlock. And circular wait. There has to be, I am waiting for A is waiting for C, and C is waiting for A circular. All of these four cases should hold, all of them, not one of them, all of them, for a deadlock to happen. If one of them is missing, okay, if one of them is missing, then deadlock will not happen. Remember the ordering the resources. Ordering the resources will eliminate this one. Okay, ordering the resources will eliminate this one. Okay, no preemption. For example, what did they do with the Unix printer queues, printer spooling? Remember the printer spooling? You tell the printer spooler, print this file for me. Only the printer spooler can print files. Nobody else can print it, okay? So only the printer spooler can access the printer. That means what? It is no preemption for the printer because nobody is using printer other than the spooler. So they have eliminated the deadlock over the printer because printer is something that doesn't need to be preempted. So there is no printer deadlock on Unix system because of the spooling. Okay, so if you design your operating system in a careful way, you will introduce one of these to your system, and that will prevent lots of deadlocks. Okay. Okay. And after that, as I said before, there will be lots of algorithms to talk about the deadlocks. For example, let's look at this one. Okay. I have three processes A, B, C, and I have three resources R, S, T. If I request R, then request S, and release R and release S, and doing this and doing this, by looking at this picture, it is difficult to see if there is a deadlock. But if I draw a graph like this, these are the processes, these are the resources. After this sequence, if I get a see the cycle in the graph, this is a cycle, right? A complete cycle. There is a deadlock. So form this graph like this and run a cycle detection algorithm, and you have your deadlock. But cycle detection algorithms are very expensive to run all the time. And making these graphs all the time is not going to be easy. So I just ignore it. If I have such a case, all of these processes will hang up. And once the user realizes that these processes are hanging up, the user will run again. Okay? They will run then again. Okay. Usually we follow this rule number 1. Ignore the problem, maybe it will go away. This is how we solve the deadlock problems in Unix, Windows, and Apple operating systems. More complicated stuff, detect and recover, dynamically avoid it, prevent your design your operating system in a way that you prevent it. We mostly do 1 and some 4. Okay, and usually they call the number 1 as the ostrich algorithm, deve kuşu algoritması. Stick your head in the sand and the problem will go away. That's the, well, by the way, I mean, ostriches, they never do that. They are not afraid of anybody. They are so strong, okay? When they see somebody, enemy, a wild animal approaching, they just kick them, right? So nobody knows why they are calling this ostrich algorithm, but the idea is this, and we follow this algorithm. We like it a lot. Okay, let me show you a few examples about, for example, deadlock detection. So these are the steps. At the end of my graph formation, this is what happens, and detect the cycle, and here is my cycle. So there is a deadlock. That's one thing. Okay, algorithm for detecting deadlocks. I'm not going to give you these algorithms. It's like, remember your Dijkstra's algorithm, shortest path algorithm, or Prim's spanning tree algorithm. They are like that. Okay, this is your graph, and you do this and that and that, and usually O n square log n algorithms, expensive algorithms, and you are supposed to run this in your kernel, and then it becomes more complicated if you have more than one scanner and one printer. You have 3 printers and 5 scanners. Okay, detecting a deadlock in this case is going to be even more difficult, and usually we use the matrices for the simple cases, but for complicated cases, okay, for complicated cases, we use algorithms like Banker's algorithm. Okay, I have many resources. I have many numbers for each resource. Banker's algorithm, don't forget this name. Okay, very widely used, but very rarely, very widely cited. Every operating system book reserves maybe 10 pages, 5 pages for this algorithm. Very elegant, nice algorithm, but nobody uses it. You will get questions from interviews about this algorithm, maybe. So remember the name. Okay, circular weight conditions. Okay, I'm not going to talk about this. Okay, live lock again. See this one? Try, lock, fail. If I fail, release it, wait, and acquire lock in a while loop. Okay, this is called live lock. Both of them are active. Both of them are trying to do the same thing, but nothing is happening. Okay, good. Starvation is not deadlock or a live lock. Starvation is different. For example, no preemption. I took the CPU and I'm using it. I'm not releasing it. All the other processes are starving. Okay, because there is no preemption. It's not deadlock. I am happy, I am living, but all the others are. There are enough resources, but only one process is using the resource. The other ones are not using it. So starvation is something different. Okay, so that's basically 20-minute coverage of the deadlocks, and that will be it. And Mustafa talked about the virtualization and containers last week. I guess that will be it for the whole semester. So at the beginning of the semester, I told you that I will cover all this stuff. Let's go to the beginning of the book contents. Yeah. Okay. I said the introduction we did, like we spent lots of time. Processes and threads. Okay, it is the abstraction of the CPU, right? So how do we abstract away the details of the CPU? How do we manage our CPU? Then memory, how do we abstract away and manage our memory? Then file system is the third important concept. And after that we said that let's go into details about the input output. We talk about that. And then chapter number 6 was deadlocks. I just skipped over it a little bit. Virtualization and cloud. If I had more time, I would have talked about this one even more, but I didn't have time. Rest of the book is about, can I make this bigger? Multiple processes. Usually we discuss about these at our graduate level course, okay, operating system, advanced level course, operating system course, and then we have the security is important too, of course. And that's it. And then the book talks about case studies about Linux, Unix, and Android. When you read about these chapters, it will tell you about how they solve the problems about the CPU abstraction in Unix or Minix or Windows and etc. Okay, so this is about Linux, and then Linux and Windows. I think I have a separate chapter about Windows, and that's it. That's it for the whole book. So if you have time, read the rest of the book during your summer studies. That will be very useful for you. Okay, I think tomorrow is the last day for your homework number 3, and homework number 2 is ready. It will be in 15 days. I might assign an optional homework number 4. Okay, an optional if you miss one of the homeworks. I may not, I don't know. That will be, I think, our final date is June 13th. Is that correct?
Yes.
June 13th. So follow the announcements. That will be it. Okay, thank you. That's it.